Let's begin this lesson by looking at linear velocity. Linear velocity is the rate of change of the position of an object, usually with respect to time. So if we had a vehicle that traveled forward over a certain distance, let's say that distance was 110 miles, and it took 2 hours to get there, we could compute the average velocity by taking the 110 miles and dividing it by 2 hours, and we could compute it to be 55 miles per hour. Now, I'm not saying that the vehicle was always traveling 55 miles per hour. I'm saying the vehicle was traveling on average 55 miles per hour. Sometimes it would be below that amount, especially at the start of the vehicle's travels, and it would maybe go faster at some point. In fact, if we would look at it at, let's say, the 1.2 hour mark, and we wanted to find what the velocity was at that instant, we would call that instantaneous velocity. And for that, we might look at the speedometer, and it might even read 60 miles per hour, faster than when we were actually going over its average. We can better understand average velocity compared to instantaneous velocity by looking at the graph with the black curve, in which miles traveled is a function of hours driven. Let's go back to the average velocity over the time interval from 0 to 2 hours. When we compute the average velocity, we are saying the vehicle could travel at a constant rate of 55 miles per hour for those 2 hours, a direct variation. This value is also the slope of the secant that passes through the points 0, 0 and 2, 110. During that time, the speedometer would always show the velocity at 55 miles per hour. But since the graph is a curve that does not follow the secant line, the speedometer would not always show 55 miles per hour. In fact, the speedometer would show a much lower value at the beginning of our drive, as we are proportionally traveling less distance over the same proportional amount of time. And as we get closer to the end of the 2 hours, our rate is faster than the slope of the secant line. So when we wish to find the instantaneous velocity at time equals 1.2 hours, we need to find the slope of the tangent line that passes through the curve at that moment. But how do we find that value mathematically? The most reasonable approach is to find the average velocity over shorter and shorter periods of time. For instance, when I computed the average velocity over 0.4 hours to 1.2 hours, I found it to be 54.4187 miles per hour. Now, if you look at the graph above, the green secant line for those 2 points is closer to the blue slopes representing average velocity than it is to the red slope of instantaneous velocity. But as I reduce the time interval, keeping one of the endpoints always at 1.2 hours, each new green secant slope moves closer to the tangent line slope, just as each computed average velocity gets closer to 60 miles per hour. Now, if I was to use time intervals that occur after 1.2 hours, for instance 1.2 to 2 hours, the average velocity, along with the green secant slope above, might be greater than the instant velocity. But again, as the length between those two endpoints of time get closer to 0, our average velocity keeps getting closer to 60 miles per hour. So, it appears that the average velocity can get as close to 60 as we like by taking time intervals in which the one varying endpoint is close enough to 1.2 from either side. And from that, we can assume that our instantaneous velocity will be 60 miles per hour. Let's go beyond velocity and look at rates of change in general. And we'll begin with average rate of change, which I'll refer to quite often as slope based on 2 points. We can also have a more formal definition in which we look at the slope of a secant line. A secant is a line that passes through 2 points on a curve or function, which means we'll go back to our old traditional slope formula, except I'm going to make some small modification. Instead of y's, we'll look at f of certain values, x1 and x0. And that difference between those two heights will be called delta f, or the change in the f's. Just as the x0 and x1 are x coordinates, the change between those coordinates will be delta x. Just remember, x1 cannot equal x0, otherwise you're going to have 0 in the denominator. Which kind of leads to our next one, which is the instantaneous rate of change, which I'll refer to quite often as slope based on 1 point, or slope of a tangent line. Tangent is a line that passes through 1 point on a curve or function. So if we were to take 1 point and apply it using our old formula, well, we would end up having f of x0 being subtracted by itself, just as x of 0 is being subtracted by itself. And we would get 0 divided by 0, which is a big problem. So what we do is what we're going to do is find the limit of the average rate of change. So we have to find the limit of delta f over delta x as delta x, that change in the x's, gets closer and closer to 0.